Let me ask you something stupid. Why does a flame point up? Light a match. Light a candle. Light a campfire. The flame goes up. Always. Tip the candle sideways, and the flame bends and curls and finds its way back to pointing up. Hold the match upside down, and the flame still climbs toward the ceiling like a little orange tongue trying to lick the sky. It is one of those things you have seen 10,000 times in your life and never thought about for half a second, because the answer feels obvious. Heat rises. Everybody knows that. Heat rises. Done. Next question. I want you to hold on to that answer for a few minutes. Hold it tight. Believe it, because it is wrong. Or, all right, fine, it is not exactly wrong, but it is hiding something. It is doing a kind of magician's misdirection on you, and once you see what it is hiding, I think you will never look at a candle the same way again. Here is the punchline I am going to spend the next half hour earning. If you take a candle, and you light it, and you put it somewhere where there is no gravity, the flame does not point up. It does not point sideways. It does not point. The flame becomes a little glowing ball, a pale blue sphere of fire, sitting in the middle of the air going absolutely nowhere. It looks like a tiny dim moon. It barely makes any light. Sometimes you can hardly see it at all. That is a real thing. People have done this experiment. Astronauts have lit candles in spacecraft and watched a sphere of fire form, just hanging there in the cabin, while the astronaut floats next to it and writes down notes. And the question I want to chew on with you is, what on earth is going on? Because that simple shape, that glowing ball, is telling us something profound about what fire actually is. Something most people, including most people who have lit 1,000,000 matches, have never thought about. So let us go back to the stupid question. Why does a flame point up? Let us pretend we do not know. Let us be genuinely confused, the way a curious child is confused, and let us follow the confusion wherever it leads. Because I promise you, by the time we are done, that little flame in front of you is going to look like a much stranger creature than you ever suspected. All right. Step 1. What is a flame? Stop and try to answer that. Out loud even. What is a flame? You might say, well, it is fire. Okay, fine. What is fire? It is hot stuff. It is burning. It is what happens when something burns. Right. But what is the thing? What is the actual physical object? Watch a candle for a minute. There is the wax. There is the wick. There is, above the wick, this dancing teardrop of light. Reach toward it, and you feel heat. But the teardrop itself, what is it? Is it a thing? Is it stuff? Is it matter? Sort of, but not really. It is more like a process, wearing the costume of a thing. A flame is not an object the way a rock is an object. A flame is an event that has been going on long enough to look stable. It is a chemical reaction made visible. It is a region of space where stuff is happening, and the stuff happening produces light, and the region of space stays in roughly the same place, so we treat it as a thing. But it is not. It is a doing, not a being. Let me explain what is doing. The wax in the candle is mostly long carbon chains. Hydrogen and carbon hooked together in chains, sometimes 20 or 30 atoms long, in a kind of waxy molecule. The wick soaks up the melted wax, the way a paper towel soaks up water. The heat from the existing flame turns that liquid wax into a vapor, an invisible gas rising off the wick. That gas, the wax vapor, mixes with oxygen from the air. And when the temperature is high enough, the molecules of wax vapor and oxygen smash into each other hard enough to break apart and rearrange. Carbon hooks up with oxygen. Hydrogen hooks up with oxygen. You get carbon dioxide. You get water. And along the way, you get a tremendous amount of heat and a tremendous amount of light. So a flame is a place. It is a place where wax vapor meets air, where the temperature is just right for them to react, where new molecules are forming as fast as the old ones can come in. It is a chemical kitchen with no walls, hovering in midair, replenishing itself at exactly the speed it consumes itself. Now look at the flame again with that picture in your head. The bottom of the flame, right above the wick, is dark. There is almost a little hollow space there, a tiny void you can see if you look closely. That is wax vapor, freshly evaporated, not yet hot enough to react. Then surrounding that is a faint blue zone. That is where the chemistry really kicks off, where oxygen first meets the fuel and starts breaking it apart. Then around the outside you have the bright yellow-orange tear shape that you actually call the flame. That bright part is not the chemistry itself. That part is soot. Tiny black specks of unburned carbon, glowing because they are hot, just incandescent particles, like the filament in a light bulb, but suspended in midair, formed and consumed as the flame breathes. So when you look at a candle, you are looking at a layered thing. Cool fuel in the middle. Hot reaction in a thin shell around it. Glowing soot around that. And the whole assembly is shaped like a teardrop. Pointed up. Why pointed up? Heat rises. Right. We agreed on that. Hold on to it. We are about to start poking it. Why does heat rise? That is the question. Most people, if you push them, will say something like, well, hot air is lighter than cold air, so it goes up. Okay. That is in the right neighborhood. But what does that even mean? What does it mean for one thing to be lighter than another, and so it goes up? Air is air. Why does air care? Imagine a swimming pool. Picture it. A pool full of water, summer afternoon, kids splashing. Now imagine I take a beach ball, push it underwater, and let go. What happens? It shoots up, comes flying out of the water like a little rocket. We have all done that as kids. The beach ball goes up. Why? Because the beach ball is less dense than the water. There is less stuff packed into the same volume, so the water surrounding it is heavier, and gravity is pulling on everything. Gravity is pulling the water down, and the water down, and the water has to go somewhere. So the water around the ball squeezes inward, gets under the ball, and shoves the ball out of the way as it falls. That is what we call buoyancy. The ball does not really want to go up. The water wants to go down, and the only way down for the water is to push the ball out of its way. Same thing in air. Hot air is less dense than cold air. The molecules of hot gas are bouncing around faster, flinging each other apart, taking up more room. Same number of molecules, more space. So a packet of hot air is like a beach ball under cold air water. The cold air around it, pulled down by gravity, falls past the hot pocket, gets underneath it, shoves it up. The hot air goes up because the cold air is going down and there is nowhere else for the hot stuff to be pushed. That is buoyancy. And here is the part everybody glides past, the part that I want to grab you by the shoulders and shake about. Buoyancy is gravity. Buoyancy is gravity working on differences in density. Take gravity away, and there is no down. And if there is no down, there is no up. And if there is no up, hot air does not rise. There is no rising. The whole concept does not exist anymore. Think about that. Heat rises is not a property of heat. Heat rises is a property of being on Earth. If you took a closed jar of perfectly still air and you let it just sit, the cold air would not be at the bottom and the hot air would not be at the top, because there is no bottom and there is no top inside that jar. There is just air, pulled by gravity, and the denser stuff settles. That is not the air making a choice. That is gravity making a choice for it. So a candle flame, sitting in your kitchen, is being shaped by gravity. The little teardrop of fire, that little pointed shape, exists because gravity is reaching into the room and grabbing the cold dense air and pulling it down past the hot reaction zone. The cold air slides down along the sides of the flame, gets under the flame, and pushes a column of hot reaction product upward. That column carries away the hot soot, stretches the flame out into a long, thin, pointed shape, and dumps the heat and the carbon dioxide up toward the ceiling. Without that column of falling cold air, the candle could not even breathe. Let me say that again. The candle cannot breathe without gravity. The way a candle gets its oxygen normally is that the column of hot rising air leaves a kind of low-pressure pocket, and fresh cold air, full of oxygen, falls in from the sides to fill it. The candle is being fed by buoyancy. The flame is sucking new oxygen in by virtue of sending old combustion products up. The whole shape of the flame is a chimney, a miniature self-sustaining chimney made of the air itself. Take that chimney away, and the candle starts to suffocate. This is going to come back. Hold it. Now, before we leave Earth and go to space, I want to stop for a minute and tell you about one of the greatest demonstrations in the history of teaching. There was a man named Michael Faraday, an Englishman, born poor, mostly self-taught, the son of a blacksmith, who became one of the greatest scientists who ever lived. And every Christmas, in London, Faraday would give a series of lectures for children. Just children. He would stand up at the lecture hall and demonstrate experiments and explain physics. And one year, in 1860, Faraday gave a series of 6 Christmas lectures titled The Chemical History of a Candle. 6 lectures about a candle. Just a candle. A little stick of wax with a string in it. He pulled more out of that candle than most professors pull out of an entire textbook. He showed how the wax was a hydrocarbon. He showed how the wick capillaries worked. He showed what the dark zone was, what the bright zone was, where the soot came from. He proved that the flame produced water by holding a cold spoon over it and showing the condensation. He proved it produced carbon dioxide by collecting it and tipping it out into lime water. He weighed the candle. He timed it. He cut it open. He brought the candle indoors, took it outdoors, lit 2 of them at once, watched their flames join. And out of all that, 6 lectures worth, he laid out almost the entire architecture of basic chemistry. From a candle, Faraday said the candle was the perfect entry into science because it had a little bit of everything in it. A little physics, a little chemistry, a little fluid mechanics, a little optics, a whole universe sitting on a table in the dark. He said something to the effect of, "You cannot study a candle and not become a philosopher." I want you to hold that idea. Faraday looked at a candle and saw the entire physical world in it. He did not yet know about microgravity. Nobody had been to space, but he had already figured out that the shape of the flame, the up-pointing teardrop, was due to a current of air rising through it. He even drew it. He drew a candle with arrows showing cold air flowing in from below and hot air streaming out the top. He understood, in 1860, that a candle is a chimney. He just had no way to test what would happen if you turned the chimney off. We can test it. We have tested it. And the answer is wild. Let us turn the chimney off. Let us go to space. Imagine you are floating inside a spacecraft. Everything around you is in free fall. The whole vehicle is falling around the planet. And you and the air and the walls and the candle are all falling at exactly the same rate. So inside the cabin, things just float. There is no down. If you let go of a pen, it stays where you let it go. If you blow a puff of breath, it does not fall, it does not rise, it just hangs there as a little rotating cloud of warm air, very slowly mixing with the rest of the cabin. Now strike a match. You can. It works. The chemistry of the match head, the friction, the little flare of phosphorus, all that works fine. None of that depends on gravity. The match lights, and you get a little burst of orange flame. But the flame in your hand looks wrong. It does not climb. It does not lengthen. It does not point. The first thing it does is shrink. The bright part contracts down toward the match head, and what is left is a little rounded pillow of pale yellow blue, sitting around the match like a ghost. There is no teardrop. There is no plume. There is no smoke trail. Just a smudge of light that fattens into a ball. Hold the match still, and the ball gets rounder. It is not a sharp ball. It has a slight bluish edge and a dimmer yellow interior. It is dimmer than any candle you have ever seen. It is so dim in some experiments that the cameras barely pick it up. It is only a few centimeters across, and it does not move. Then, after a few seconds, it goes out. It just smothers itself. Why? Because the chimney is gone. The candle, on Earth, breathes by buoyancy. The hot air goes up, the cold air falls in, and that flow constantly delivers fresh oxygen to the reaction zone and sweeps away the carbon dioxide and water vapor. Take away gravity, and the hot air does not go up, because there is no up. The combustion products just sit there. They form a little envelope around the flame, choking it. The fresh oxygen cannot get in. The exhaust cannot get out. The flame is sitting in its own breath. The only way oxygen reaches the flame, in microgravity, is by diffusion. Diffusion is the slow, random wandering of molecules from regions where there are a lot of them to regions where there are not so many. It is what makes a drop of food coloring in a still glass of water spread out over the course of hours. It is what carries the smell of bread across a kitchen even when there is no breeze. It is real, it works, but it is slow. Compared to a buoyant chimney sucking in liters of fresh air every second, diffusion is molasses. So the flame in space gets only as much oxygen as can wander into it through random thermal motion. That is enough to keep some kinds of combustion going, but the reaction is starving. It is on a diet. It is gasping. So it burns cooler, and dimmer, and smaller, and rounder. Why round? Why does it form a sphere? Because diffusion does not have a preferred direction. If oxygen has to wander in by random walk, it wanders in equally from all sides. North, south, east, west, up, down. Meaningless terms here, but you get the idea. The flame eats oxygen evenly from every direction. So the reaction zone forms a thin shell at exactly the radius where the diffusing oxygen meets the diffusing fuel vapor. And because diffusion is symmetric, that shell is a sphere. A perfect, glowing, spherical shell of chemistry. That is what fire really wants to be. That is fire's natural shape. We just never see it, on Earth. Because gravity is always there, always squeezing the sphere into a teardrop, always making fire look stretched out. The pointy candle flame is not the real thing. It is fire being yanked on by gravity. Take the gravity away, and the yanking stops, and the flame relaxes into the shape it was always trying to be. I find that almost shocking. Every fire I have ever seen in my life has been deformed by gravity. Every match, every campfire, every candle on every birthday cake, every burning leaf. They are all the same chemical process, all forming little distorted versions of the spherical truth. We have spent our entire lives looking at the warped shape and assuming it was the real shape. Now I want to slow down here, because I think the implications go further than people realize. Once you accept that gravity is shaping the flame, you start to see other things gravity is doing. For instance, the color.